The Fick's law of diffusion, enunciated by Adolf Eugen Fick in 1855, postulates a linear relationship between the diffusion flux and the gradient of concentration. The constant of proportionality is the Fick diffusivity. For a binary mixture, say the molar flux of component 1 is related to the difference between the velocity of diffusion of component 1, u sub 1, minus the molar average mixture velocity u. x1 is the mole fraction of component 1 and v sub m is the molar volume of the mixture. If we take the mole fraction gradient to be the driving force for diffusion, we may define the Fick diffusivity for a binary mixture diffusion as the scalar quantity d, and since the mole fractions add to unity, the gradients of the mole fractions sum to 0. The molar fluxes of the two components J1 and J2 also sum to 0, and there is only one independent scalar Fick diffusivity d describing diffusion in a binary mixture. For a ternary mixture, there are two independent driving forces. For example, we may consider dx1 by dz, where z is the direction of diffusion, and dx2 by dz as the driving force of component 2. There are two independent driving forces because the sum of the mole fractions add to unity. There are two independent molar diffusion fluxes, J1 and J2. And the generalized Fick's law of diffusion defines a matrix of diffusivities D11, D12, D21, and D22. In this presentation, I provide some insights into the elements of the Fick diffusivity matrix by comparing the Fick's law of diffusion with the Maxwell-Stefan diffusion formulation. Watch also my video presentations, What Drives Diffusion and Uphill Diffusion, on my YouTube channel. Let's begin by analyzing diffusion in binary mixtures of components 1 and 2. Let U1 and U2 represent the velocities of motion of components 1 and 2 in a laboratory fixed reference frame. U is the molar average mixture velocity. Since the chemical potential gradients are constrained by the Gibbs-Duhem relationships, only one of the chemical potential gradients is independent. The mole fractions sum to unity, and therefore there is only one independent measure of composition. In the Maxwell-Stefan formulation, the force acting per mole of species 1 is balanced by friction species 1 experiences in undergoing relative motion with respect to species 2. The frictional term must be proportional to the composition, and we take that proportionality to be represented by the mole fraction of component 2. The physical significance of the Maxwell-Stefan diffusivity, where we use the symbol D with a line through it, is that it represents an inverse drag coefficient. The force acting per mole of species 1 is a negative of the gradient of the chemical potential with the units newtons per mole. The Maxwell-Stefan equation can be reformulated in terms of the diffusion flux, which is defined as the flux with respect to the molar average reference velocity Vm is the molar volume of the mixture. Rather than use the chemical potential gradient as a driving force, it is convenient to define a thermodynamic correction factor given by this expression, which quantifies departure from ideality. Indeed, if the activity coefficient is unity, gamma is equal to unity, and the Maxwell-Stefan equations can be recast into the form flux of component 1 is proportional to the mole fraction gradient of component 1, and the constant of proportionality is the Maxwell-Stefan diffusivity times gamma. Therefore, in comparison with the Fick's law, we note that the Fick diffusivity equals the Maxwell-Stefan diffusivity times a correction factor that quantifies departures from thermodynamic idealities. Let us examine diffusion in the binary mixture of methanol and normal hexane at a temperature of 313 Kelvin. The Fick diffusivity is plotted here as a function of mole fraction of methanol. We note that the Fick diffusivity decreases by about an order of magnitude as composition of 0.5 is approached from either end. By dividing the Fick diffusivity by the thermodynamic correction factor gamma, we obtain the Maxwell-Stefan diffusivity, and that Maxwell-Stefan diffusivity is practically independent of composition. This is the persuasive advantage of using the Maxwell-Stefan formulation, because it shows a more predictable composition dependence than does the Fick diffusivity. Now let's try and understand this reduction in the Fick diffusivity value as shown by the experimental data. The mixture of methanol and hexane undergoes phase splitting at temperatures below about 308 Kelvin. The green line represents the binodal curve, which is defined by the minimum in the Gibbs free energy, say at 290. These are the 2 points here where the partial derivative of G with respect to the composition x1 is 0. Those are the points. So plotting the minima in the Gibbs free energy versus composition curves, we can construct the binodal curve. The red line represents a spinodal curve. These are points at which the thermodynamic correction factor is 0. This is the same as stating that the second derivative of G with respect to the mole fraction is 0. So those are the points representing the spinodal curve. Within the region, the mixture will undergo phase splitting. Say if we take a composition here of 0.5, subject to a small perturbation, the mixture will yield a hexane-rich phase and a methanol-rich phase. The area between the spinodal curve and the binodal curve is a metastable region. A different way of expressing the phase splitting phenomena is to say that the Fick diffusivity is negative in this region. Now, the sharp decrease in the Fick diffusivity is due to the fact that at this temperature 313, we are very close to the two-phase region. Now, the phase splitting in liquid mixtures occurs too quickly or too fast in order for us to follow the diffusion trajectories. The Maxwell-Stefan diffusion equations for non-ideal ternary mixtures can be written in the usual manner. For species 1, for example, the force acting per mole of species 1 is balanced by the friction it experiences with species 2 and with species 3. And similarly for the force acting on species 2. The Onsager reciprocal relations demand the symmetry that D12 equals D21. So there are 3 independent Maxwell-Stefan diffusivities, and these are composition dependent. We will see later that these can be estimated from the tracer diffusivity data. The second law requirement demands that the Maxwell-Stefan diffusivities be positive definite. An important advantage of the Maxwell-Stefan formulation as opposed to the Onsager formulation is that the Maxwell-Stefan diffusivities Dij do not depend on the choice of the reference velocity frame. These equations can be recast into the Fickian form by using two-dimensional matrix notation. The column matrix of diffusion fluxes is related to the column matrix of mole fraction gradients, the constant of proportionality being a square matrix of Fick diffusivities. The expression for the matrix of Fick's diffusivities can be derived, and this consists of a product of two matrices. The first one contains only the Maxwell-Stefan diffusivities, and this matrix is multiplied by another square matrix containing the thermodynamic correction factors gamma 11, gamma 12, gamma 21, and gamma 22. The thermodynamic correction factors can be estimated from available data on thermodynamic phase equilibrium, say using the NRTL equation or the Flory-Huggins equations for polymeric systems, CalFAD for metallic alloys. Let's gain some understanding on the behavior of diffusivities in the non-ideal ternary mixture of glycerol, acetone, and water. This system has a region in which we have phase separation. The green line represents the binodal curve, and the red line denotes the spinodal curve. Along the spinodal curve, the determinant of the matrix of thermodynamic correction factors is 0, and consequently, the determinant of the Fick diffusivity matrix is also 0. Let's look at the elements of the matrix of Fick diffusivities as we move along this line from composition A to composition B to composition C to composition D. For composition A, the elements of the matrix of Fick diffusivities has these elements, and if we take the product of the cross coefficients and divide by the product of the diagonal elements, the ratio is found to be 0.01725. This ratio increases as we approach the region of phase immiscibility. And consequently, the magnitude of the coupling effects increases as we approach compositions close to phase separation. This has severe consequences for composition trajectories in regions close to the two-phase region. The entire set of experimental data of Grossman for the elements of the Fick diffusivity matrix in the homogeneous phase regions of the ternary mixture glycerol, acetone, water are replotted in this diagram. The y-axis represents the relative coupling effects of the D matrix, and this is expressed as the product of the cross coefficients divided by the product of the diagonal elements. The x-axis represents the relative coupling effects in the thermodynamic correction factor matrix that is calculated using the NRTL model, and the relative coupling effects are described by the product of the off-diagonal elements divided by the product of the diagonal elements. We note that there is a good correlation between the relative coupling of the Fick diffusivity matrix with the relative coupling effects due to thermodynamic correction factors. We conclude that thermodynamic coupling is the major contributor to diffusional coupling in organic liquid mixtures. Also notable is the fact that these coupling effects increase and are maximum at the spinodal composition, which is plotted by the stars here. This expression for the elements of the matrix of Fick diffusivities as a product of two matrices can be used to estimate the elements of the Fick diffusivity from information on diffusivities in the corresponding binary mixtures of the pairs glycerol water, glycerol acetone, and acetone water. For example, experimental data on the Fick diffusivities for the system acetone water are shown by the red circles. By dividing the Fick diffusivities by the correction factor gamma, we obtain the Maxwell-Stefan diffusivities, and the Maxwell-Stefan diffusivities indicated by the green squares shows a predictable composition dependence, and these can be estimated, say, using a interpolation formula on the basis of the self-diffusivities at either end of the composition range. So similarly, D13 can be estimated from experimental data on diffusivities in the binary mixture 1 and 3, and from the binary mixture of 2 and 3. So this matrix can be estimated from the constituent binary pairs. The matrix of thermodynamic correction factors can be estimated from, say, the uniquac or NRTL parameters for phase equilibrium. And this affords a straightforward procedure for estimation of the Fick diffusivities. Consider the experimental data reported in 1985 for interdiffusion in the system glycerol, water, and acetone. These experiments were conducted in a Lewis stirred cell. The bottom cell contains a mixture of glycerol and water at this composition. The top cell contains a mixture of acetone and water at this composition, and at time t equals 0, the stirrers are rotated and interdiffusion is allowed to take place. The experimental data showing the approach to equilibrium is shown by the open circles in either phase. If we join this point with the initial point here, the mixture composition ends up in the two-phase region and the phases will equilibrate to the compositions shown at the end of this tie line. So in the glycerol-rich phase, the equilibration trajectory is from x0 to xeq, and in the acetone-rich phase, the equilibration is along this line. Note that the trajectories are not linear, but curvilinear or serpentine. The blue lines show the model calculations using data on the Maxwell-Stefan diffusivities and thermodynamic correction factors calculated from the NRTL parameters and information on the diffusivities of the corresponding binary pairs: acetone water, water glycerol, and acetone glycerol. So the serpentine trajectories can be predicted from the data on thermodynamic non-idealities, along with data on the diffusivities of the corresponding binary pairs. The message to be drawn here is that serpentine trajectories are the result of diffusional coupling effects that are engendered largely by thermodynamic coupling effects.